So welcome to the next topic, or in this unit, solids, liquids and gases. Now most of this content will be for the Triple Science Award, okay, and this will be in the red type. Shouldn't really be a problem for most of us are doing triple anyway. So what are we going to learn? Well, there's basically two areas. We're going to look at change of states, okay, which will link closely to probably what you're studying in chemistry, and also the ideal gas molecules, which again will link with what you've been doing in chemistry. Okay, so there's a bit of crossover between the two subjects. So these are the learning objectives that you should have achieved by the end of the lesson. So states of matter. So as you now know, substances can exist as solids, liquids, or gases. So solids, in a solid, as you can see from the diagram here, the particles vibrate around fixed positions. They do move, but they just vibrate in fixed positions within a closely packed structure. So the particles are very close together. The particles therefore cannot move except in their vibrations. And this results in a solid having a definite shape and a fixed volume. Okay, so a cube of lead doesn't start wandering about. Then we have the liquids. Okay, so when a solid is heated, it may melt to form a liquid. So when ice melts, it forms liquid water. And what happens there is that the liquid, in the liquid, the particles move in between each other. They're beginning to move more freely. And they're approximately the same distance apart as they would be in a solid. But they have more freedom of movement, slightly more freedom of movement. A liquid doesn't have a definite shape, but it does have a fixed volume. Okay, so basically if you put a liquid into a container, it will take the shape of the container. Then we finally have gases, because we won't do plasma this year. Gases are, again, so now you're heating the liquid. They gain kinetic energy, and the gas forms which can basically the liquid boiling or evaporating and turning into a gas. So in the gas, the particles move in between each other and are further apart than they are in the liquid. They also move a lot faster. Okay, and what happens is the gas takes the shape or volume of the container. Okay, so it doesn't actually have a definitive shape like a solid would. Okay, so this table here basically summarizes the properties of solids, liquids, and gases. Okay, so solids have a definite shape, liquids and gases do not. Solids cannot be compressed and liquids cannot be compressed, but gases can. Solids and liquids are relatively dense compared to gases. Solids cannot flow, but liquids and gases can. Solids and liquids do not expand to fill a container. Okay, the distance between in a liquid distance between the particles doesn't increase, but in the case of gases it can. So no, yes. And solids are a fixed volume, whereas gases aren't, but liquids are. So this is basically how we get between the three different phases. So solids melt to form liquids, which then evaporate or vaporize to form gases. That gas then can deposit to form a solid, and the cycle begins again. Or the gas can condense to form a liquid, and the liquid then solidifies to become a solid, and the solid can go straight to a gas in the form of sublimation, which you see with solid carbon dioxide. So there's no such thing as liquid carbon dioxide. It goes from solid carbon dioxide straight to the gas. So these is to complete this kind of review of what you probably learned previously in chemistry. Choose an appropriate word to fill in the gaps. So a solid has a definite shape due to it consisting of closely packed molecules which can move in between each other. When a solid is heated, it becomes a liquid. The molecules can move in between each other now. They can flow. However, the molecules remain close together, and so a liquid is dense and incompressible, just like a solid is. When a liquid becomes a gas, the molecules fill up the space available. Therefore, the gas can be easily compressed. So in terms of gases now, and we've touched on this in the previous unit in this topic, basically a gas consists of a molecule moving around randomly, okay, and there's an animation of it there. These blue and red gas particles are moving randomly in the container. Due to collisions, the speed and direction of each molecule is continually changing in an unpredictable way, as you can see from the animation. So this leads us on to something called Brownian motion. Okay, so here in this animation we have the yellow sphere representing something called a pollen grain. So you may have looked at this in biology. And the black particles represent water molecules. So basically this is a pollen grain dropped on in some water, basically. Okay, and this is on the surface. So in 1827, Robert Brown observed through a microscope the motion of pollen grains suspended in water. The grains, as you can see by the animation and the kind of blue line, you can see that they're basically moving around randomly. And you can also see a similar observation when you have smoke particles suspended in the air. So what's significant around Brownian motion? Well, Einstein, that famous physicist, in 1905 proved that the motion of these small, invisible, in this case, water molecules, if you're talking about pollen grains, must be random as the larger visible pollen grain. And the pollen grain or smoke particles move much more slowly than the water or air molecules due to their greater mass. Okay, so what does this have to do with gas pressure? Well, the particle theory of gas explains gas pressure in the following way. Okay, so that's a diagram we've probably already seen earlier in the topic. So gas molecules are in constant random motion. Okay, we know that now. Okay, that's Brownian motion. So when a molecule collides with a surface, it exerts a force on the surface as it changes direction. Okay, so there's now a force being exerted here on this surface. And obviously the surface, according to Newton's third law, is also exerting a force in the opposite direction, which causes the particle to move away. So the pressure exerted by the gas is equal to the total force exerted by the molecules over an area of the surface divided by that particular area. Okay, so we've already looked at that in terms of pressure. So pressure equals force divided by area. So that's going to be linked to three different laws from the late 18th, early 19th century, which you have to become familiar with. And the first one is Boyles Law. So Boyles Law states that the pressure of a gas is inversely proportional to its volume. So what does that mean? Well, it means that if the volume of the gas is doubled, then pressure will be halved. Okay? So Boyle's law only applies for a gas if its mass and temperature are kept constant while the volume is being changed. Okay, so Boyle's law states that pressure equals 1 over the volume. Okay, that's what Boyle's law states. There we go. So you can rearrange our equation to state that P1 times V1 equals P2 times V2. Where the pressure 1 is the initial gas pressure, pressure 2 is the final gas pressure, pressure 1 is the initial volume, and the final gas volume is V2. Okay, so now let's use the equation we've just learned to answer a question. So a gas has an initial volume of 30 meters cubed, okay, an atmospheric pressure of 100 kilopascals. Calculate the final pressure if its volume, so we're going to calculate the final pressure. The gas of the volume is decreased, the volume of the gas is decreased by 10 meters cubed. Okay, so pause the video now and then come back when you think you have the answers. Right, so obviously you break down the question. So the gas has initial volume, so this is V1 here, this is P1, that's going to be P2 here, and that's going to be we don't know what that is, and that's going to be V2. Okay, so we have to plug in the equation. So P1 times V1 equals P2 V2. So we just got to find P2. So 100 kilopascals times 30 meters cubed equals P2 times 10. Okay, so 3000 kilopascals will equal 10 P2. So therefore P2 equals 3000 kilopascals divided by 10, which if you do the calculation gives you a final pressure of 300 kilopascals, which it makes sense in a sense, because the volume has decreased. Okay, so it means that because you just squish down the gas particles, it should have an increased pressure. So you can check Boyles Law experimentally using basically a pressure gauge and a scale. So you record the initial volume and pressure of a gas in a tube, and then use the foot pump to decrease the volume of the gas in the tube, and then record the new volume and pressure. So you then use the foot pump the second time to obtain further sets of volume and pressure measurements to get an average. So you can therefore do a plot of a graph. So you can then plot a graph of pressure against 1 divided by the volume, okay? Because you're changing basically the pressure by changing the volume for several values. And you should get a straight line through the origin. That means that Boyles Law would be true. Okay, so Boyles Law is confirmed if the set of volume and pressure measurements give the same answer when multiplied together. So P times V should be a constant. So if you do a pressure and volume graph, you get a curved line like this, okay? And what that's basically saying is that the line doesn't intercept either of the axes, which is an example of a inverse relation. Okay, so now I want you to draw the following table and complete it. And the equation, of course, is P1 V1 equals P2 V2. So using that equation, answer the following questions by completing the variables that are missing. Be careful, of course, when you're converting kilopascals, and good luck. Once you've completed it, restart the video and see if you've got the correct answers. Okay, so welcome back. So P1 is 100 kilopascals. The volume of the container is 30 centimeters cubed. The pressure then becomes 600 kilopascals. What is the new volume? Well, the pressure is increased, so I'm assuming the volume decreases, and that's indeed the case. It's now 5 centimeters cubed. You've kind of crushed it. Okay, so if the pressure now is 100 K and 30 centimeters cubed, but this time the volume of the container has increased, then the pressure is then reduced to 200 kilopascals. If you reduce the volume of the container to 25 at the start, and the pressure of the container at the end is now 20 kilopascals, so the pressure has been reduced even further, then the volume must have increased, and indeed it has, is 125 centimeters cubed. If you further reduce the volume of the container to 20 centimeters cubed, and then change it to 80 centimeters cubed, so you've increased the volume, then the pressure should go to 25 kilopascals. And if you halve the pressure at the start, and then decrease the volume or increase the volume to 20 centimeters cubed, and the pressure goes up, so I'm assuming it's going to be decreased, and indeed it's the case. It's now 60 centimeters cubed, okay, compared to the volume of 20 centimeters cubed at the end. That's why the pressure's gone up. And finally, if the volume is now 10 centimeters cubed at the start and 100 kilopascals at the end with a volume of 50 centimeters cubed, it means the original pressure must have been 500 K. Okay, so now we're going to choose the appropriate words to fill in the gaps below to summarize this particular topic. So as a gas consists of particles called molecules that are in constant random motion. The pressure of a gas is caused by the force exerted by the molecules when they collide and rebound off the surface experience the pressure. According to Boyles Law, the pressure of a gas multiplied by its volume is equal to a constant number provided the temperature of the gas does not change. And that is Boyles Law. The next subject or area we're going to look at is absolute zero. Okay, so as temperature decreases, the average speed of which molecules move also decreases. Eventually you get to a temperature where all molecules stop moving, and that temperature is called absolute zero. So absolute zero has a temperature in degrees Celsius of minus 273 degrees Celsius. Okay, well exactly 273.15, but who's kind of counting? So it's not possible to achieve this temperature, okay, because it's just no way on Earth you can actually get this temperature. Even the universe itself is a background temperature of about minus 269 degrees Celsius, 270 degrees Celsius. So the record temperature at the moment, or since 2012, is minus 273.149999999999999900 degrees Celsius. So pretty cold, but not quite absolute zero. So one thing you have to do is be able to move between the Kelvin and degrees Celsius temperature scale. Okay, so the Kelvin scale starts from absolute zero, so 0 Kelvin or 0 K is minus 273 degrees Celsius. A change of 1 Kelvin is the same as a change in 1 degree Celsius. Therefore, 0 degrees Celsius, the temperature which ice melts or ice forms, is plus 273 Kelvin. 100 degrees Celsius is 373 degrees Celsius. Therefore, Kelvin temperature can be converted into degrees Celsius temperature by just simply adding 273 to the number. Okay, so it's incorrect to say, all right, degrees Kelvin. It's just Kelvin. So, complete the following table. So pause the video now, create the table, and see if you get the correct answer. Right, so intergalactic space has a temperature of 3 Kelvin, which is equal to 270 degrees Celsius, quite cold. Vostok in Antarctica in 1983 got pretty cold. It was minus 89 degrees Celsius, which was 184 Kelvin. The average Earth's surface is 288 Kelvin, which is equal to 15 degrees Celsius. A gas flame has a temperature of about 1500 degrees Celsius, which is 1773 Kelvin. And the surface of the sun is about 6000 Kelvin, which is 5727 degrees Celsius. So what's that going to do with gas pressure? Well, you need to use Kelvin when we're discussing the relationship between it and temperature. So as temperature increases, molecules gain kinetic energy, they move more quickly. There we go. So that's a cold gas, they're kind of sluggish, whereas in a hot gas, they're moving a lot faster. Okay, therefore, if they're moving a lot faster, force equals mass times acceleration, so it's going to exert a greater force on the surface of the container, creating a greater pressure. Okay, so now we're going to look at this idea of kinetic energy and how it relates to temperature. So we're going to look at it in the case of the kinetic energy of molecules. So as temperature increases, the average speed and kinetic energy of the molecules increases because remember that kinetic energy equals half mv squared. So if we're increasing the speed or velocity of the molecules, then the kinetic energy is going to increase. Okay, so with an ideal gas, the average kinetic energy of the molecule is proportional to the Kelvin temperature, or EK, and this is the proportional sign, is proportional to temperature. So as the temperature increases, so will the kinetic energy. Okay, so question 1. The temperature of a gas increased from 123 degrees Celsius to 377 degrees Celsius. What change occurs to the average kinetic energy of the gas molecules? Okay, so pause the video now and have a think about that. Right, so the initial temperature is 123 degrees Celsius, which is 150 Kelvin, and the final gas temperature is 327 degrees Celsius, or 600 Kelvin. So you've basically added more heat energy. Okay, you've increased the temperature. So the Kelvin temperature is increased by 4 times. Okay, 600 from 150. Therefore, the average kinetic energy has also increased 4 times, because remember that temperature is proportional to the kinetic energy. Question 2. When the temperature of a gas is increased from 27 degrees Celsius, the average speed of the molecules increases 3 times. Calculate the final temperature of the gas. Okay, so again, pausing the video and see if you can work that out. So, kinetic energy is half mv squared, which we know from last year. If the speed of v increases by 3 times, then the kinetic energy would have increased by 9 times, because it's v squared. Okay. Therefore, the Kelvin temperature would have increased by 9 times, because temperature is proportional to kinetic energy. Therefore, the initial temperature was 27 degrees Celsius, which is 300 K. So therefore, it must be 9 times 300 K, or 2,700 Kelvin, or 2,427 degrees Celsius. Quite hot. Okay, so then we'll have a pressure law related to this. Okay, so the pressure law states that the pressure of the mixed mass of a gas at constant volume is proportional to its Kelvin temperature. That means if the Kelvin temperature of a gas is doubled, the pressure will double. Okay, so that's basically saying that pressure of a mix, so pressure is proportional to temperature, just like kinetic energy was proportional to temperature. Okay, and we state it like this: P1 over T1 equals P2 over T2, where P1 is the initial pressure, P2 is the final pressure, T1 is the initial temperature in Kelvin, and T2 is the initial temperature, the final temperature, also in Kelvin. Be careful with the units. So let's now try and apply the equation that we've just learnt to a question. So a gas has an initial temperature of 40 kilopascals at a temperature of minus 73 degrees Celsius. Calculate the final pressure of this gas if its temperature is increased to 327 degrees Celsius at constant volume. So pause the video now and try and apply the equation we've just learnt in the last slide to this question. Okay, so the first thing I would do is break down the question. Okay, so this would be P1, this would be T1, and this would be T2, and we've got to find P1. We don't know what that is. So the equation is P1 divided by T1 equals P2 divided by T2. And the first thing we have to do is convert the temperatures into Kelvin. Okay, so T1 becomes 200 K and T2 becomes 600 K. So plugging the numbers in, we get the following equation. We rearrange it to give P2 equals 40,000 times 600 divided by 200, which will give a final pressure of 100 kilopascals. Okay, so how do we check the pressure law experimentally? We record the initial pressure of basically a container of air in a round bottom flask, and the temperature of the water bath, which is equal to the temperature of the air. So that's basically what we're doing. And then we change the temperature. Okay, so you're basically going to use the heater to increase the temperature and record this new temperature and pressure using your pressure gauge. And you repeat the experiment by changing the different temperatures. Okay, and remember that temperatures have to be converted into Kelvin. So if you plot a graph of pressure against temperature, you should get a straight line graph around the origin, saying that the pressure law has been confirmed. And the pressure law is also confirmed if each set of Kelvin temperature and pressure measurements give the same answer when the pressure is divided by the Kelvin temperature. Okay, so P divided by V should be a constant. So if you do a pressure against degrees Celsius temperature graph, you will actually end up to be able to extrapolate back to the temperature of absolute zero. Okay, because it's going to cross the x-axis at absolute zero. So now to completely test your understanding, copy and complete the following table. Remembering, of course, that P1 T1 equals P2 T2. Okay, let's see how you went. So at the start, the container has a pressure of 100 kilopascals and 300 Kelvin. By the end, the temperature has dropped to 150 Kelvin, so therefore the pressure must have dropped as well, because there's less kinetic energy, the particles are moving less force on the surface of the container. So there we go, 50 kilopascals. The next example, initially the pressure and temperature are 60 kilopascals and 200 Kelvin respectively. The pressure increases to 250 kilopascals. Therefore the container, I'm guessing the temperature has increased and it has to 800 Kelvin. Okay, at the start it has initial temperature of 800 Kelvin, which is decreased to 600 Kelvin. The pressure at the end is 120 kilopascals. So I'm guessing the pressure at the start would have been probably more. Yes, indeed, 160 kilopascals. The fourth example, the pressure at the start is 50 kilopascals. The pressure at the end is 300 kilopascals with a temperature of 360 Kelvin. So the pressure has increased, so I'm guessing that the temperature at the start would have been a bit cooler. Indeed, it was 60 Kelvin. 50 kilopascals, 27 degrees Celsius at the start. The temperature at the end is 627 degrees Celsius. So the first thing you're going to do is convert obviously to Kelvin, and you should find that the pressure should have increased to 150 kilopascals. And finally, the pressure at the start is 150 kilopascals at 450 Kelvin. The pressure goes down to 100 kilopascals, so I'm guessing it's probably cooled down to around about 300 Kelvin. And indeed, that's what's happened. So now, to complete this area, before we finish the topic, let's look at choosing the appropriate words. So when the Kelvin temperature of a gas is doubled, the average kinetic energy of the molecules is also doubled. The pressure law states that the pressure of a gas is proportional to its Kelvin temperature, provided its mass and volume remain constant. And finally, according to the pressure law, the pressure of the gas should fall to minus 273 degrees Celsius, which is known as absolute zero. There we go. Okay, so basically here are a few questions that can help you revise later. Okay, so there's a few questions, 5 questions, 6 questions, and these are a few other questions which will also help you revise when we come to that point. There we go, so there's 4 questions there. Okay, and finally here's some online simulations which can help you reinforce the learning that we've shown in today's lesson.